dynamical system. Categorical dynamical system is a pair D and phi of triangulated category D and the exact endofunctor phi. And in fact, many categorical dynamical systems can be obtained from topological dynamical systems. For instance, let X be a smooth projective variety and F be an automorphism. Then they form a topological dynamical system, X and XF, and it induces the categorical dynamical system, where this is the derived category of X and this is the derived fullback of F. And the second one is simplex. It's an example from simplex geometry, and we consider a nice simplex manifold X. I will not explain what this means, but nice enough to define Fourier category, and F be a simplex morphism. Then in this case, this topological dynamical system uses the categorical dynamical system, where this is the derived Fourier category of F, and this is an induced function. And in generally in dynamics, people study the complexity of dynamical system. Likewise, we also want to study the complexity of a categorical dynamical system. So to measure the complexity of a categorical dynamical system, we need some notion, and it is the categorical entropy. It was introduced by Dimitrov, Haiden, Katzarkov, and Kontsevich. And first, let E and F be objects of D, and T be real number, and we define delta T be F be the infimum of this number, where the infimum is taken over all partial filtrations of F plus F prime with vectors of the form, this form. And so let me explain this. So if T equals to 0, this number is just M. So what is M? It is the number of the factor of this filtration. So this filtration. So in other words, this infimum is taken over all possible ways of split generating F by E. So, and in general, if T is not equal to 0, we add some weights by these shifts. And then the categorical entropy of an exact endofunctor phi is defined by the exponential growth rate of this number. So in this case, this is some split generator G, and we apply phi several times to G, and so we measure how we measure So how I don't know how to say well so the categorical entropy measure the exponential growth rate of this number. So where when n grows. So if this number grows like e to the h n, then the categorical entropy of phi is h. So the categorical entropy measures this number, the exponential growth rate of t, g, and phi and g. And here, one is a spirit generator, and a spirit generator is an object of t such that delta 0, 0, g, e is finite for every object e. So, and then, okay, now let's see some examples, and now let X be a smooth projective variety, and now let's consider some dynamical systems on the derived category of X. And first, the categorical entropy of the shift by K functor is KT. And the entropy of the tensoring with the line bundle is 0. And the most interesting one is the final one. And for F, automorphism of X, the categorical entropy of the pullback functor is the log of the spectral radius of the induced map on the numerical growth integral. And the spectral radius is of something. Some linear map is the maximum of the exerted value of the eigenvalues of something. So, and moreover, it coincides with the topological entropy of F, which I will not explain today because it's not easy to define. So by the third one, the categorical entropy can be thought of as a kind of categorification of the topological entropy. And today I want to consider the following question. And first, let's consider phi an exact endofunctor, and assume that there are two triangulated subcategories A and B of D, such that phi sends A to A and B to B. And in this case, we can consider the restricted functors. So my question is how the categorical entropies of these restricted functors are related. So in general, the most simplest case is when A is just the whole category D. And in this case, this question asks the relationship between the entropies of the original functor and the restricted functor, but as far as I know, this is still an open problem. So, but in this talk, I will explain the following. In certain situations, categorical entropies of these restricted functors almost coincide. So I will explain later that what this certain and almost means. So today's plan is as follows, and I will first introduce some entropy type invariant using T structures and or code T structures, and we'll see their basic properties, in particular the relationship with the categorical entropy, and then finally I will apply them to the case where A and B form ST triple. So let me first review the notions of T structures and co-T structures. And first, before stating the precise definition, let's see some standard example of T structure, and let A be a ring and B be the bounded derived category of mode A, and we define B like 0. I will read this by leg, which stands for less than or equal to 0 and equal to, and this by get. So we define D like 0 to be the full subcategory of D consisting of complexes concentrated in non-positive degrees. And likewise, we define D like 0 to be the first subcategory of D consisting of complexes concentrated in non-negative degrees. And then these two subcategories is a bounded T structure on D, and its heart is equivalent to the mode A. And generalizing this situation, can define a T structure, the notion of T structure, and a T structure on a triangulated category D is a pair of additive subcategories of D satisfying the following three conditions. And in view of the previous example, these two conditions are quite natural because shift by one is kind of shifting complex to the negative degree. So these two conditions are quite natural, and maybe the third condition is maybe the most important condition, and it says that every object in D can be truncated using these a T structure. Yeah. And we say a T structure are bounded if a T structure satisfy this formula. And so it is something like so like bounded derived category case. So and for a T structure, we define the heart of the T structure by the intersection of dx 0 and dx 0. So this is kind of the 0 degree part of the complex. And we say the heart is finite if it is a length category and only has finite to many isomorphism classes of simple objects. So because the heart is an abelian category, we can consider composition series and simple objects in the heart. So here a length category. I mean by a length category the category. By a length category, I mean every object in the heart has a composition series of finite length, and we also assume that the heart only has finite many isomorphism classes of simple objects. And if the heart is finite, then you can define the following number for an object of the heart. We can define an integer lambda of E as the length of a composition series of E in the heart. And and if we have a bounded T structure on D, then every object of D has a filtration like this, where these integers are decreasing. So, and in fact, this filtration of this form is unique to isomorphism. So in fact, this EI is isomorphic to the so-called the homology minus KI's homology of E. And actually, I don't know a standard name of a filtration like of this form. So let me call a filtration of this form a T filtration of E with respect to the T structure A. As I said, a T filtration is determined uniquely up to isomorphism. Yes. And co-T structures can be defined similarly. And so before stating the precise definition, let's see some standard example. And now let again A be a ring, and this time we consider the bounded homotopy category of the category of projective A modules. And as before, we define dx 0 and dx 0 in a similar way. But this time, each component is a projective module. And in this case, these categories, subcategories form a bounded co-T structure on D, and its cohort is equivalent to project A. And generalizing this situation, we can define a co-T structure, and the definition is almost the same as that of T structure, but so what is the difference? And difference is as follows. And in the case of a T structure, they satisfy these three conditions, and in the case of co-T structure, they satisfy some similar conditions, but the difference is this green part. By changing the sign of the shift functors in the definition of the T structure, we obtain the definition of a co-T structure. But because of that change, their properties are very different. For instance, in the case of a T structure, this truncation triangle is determined uniquely to isomorphism, but in the case of co-T structure, this co-truncation triangle is not unique. So there are many exact triangle satisfying this condition. And we define cohort as the intersection of dx0 and dx0. And in this case, unlike the case of T structure, this is not an abelian category anymore, and it is just an additive category. And in this case, we say the cohort is finite if it is a correlation category and only has finite many isomorphism and classes of indecomposable objects. And in this case, if cohort is finite, then we define for an object of the cohort, we define integer sigma of E as the number of indecomposable direct summands in a direct sum decomposition of E in the cohort. So we can consider such a thing because of our assumption that is a correlation with category, and so we define sigma E like this. And also in this case, we have some nice filtration. And if we have a bounded co-T structure, then we can find filtration of an object E of the form like this. So it is same. It is a filtration of almost the same form as before, but in the case of a T structure, this was decreasing order, but in this case, this is increasing. So then again, I will call a filtration of this form a co-T filtration of E, and in this case, the co-T filtration is not uniquely determined. This basically because of co-truncation triangle is not unique. Because when constructing a filtration like this, we use truncation triangle several times. So because in this case, the co-truncation triangle is not unique, so this is also not unique. And then now let me explain how to define some entropy type invariants using T structures or co-T structures. And let first let A be a bounded T structure on D with finite height. And for an object E, let this be a T filtration with respect to the T structure. And for a real number T, we define delta hat T of E as like this. Well, this was the length of a composition series of EI. So, and we multiply some weights, which records some shift data. And then for an exact endofunctor, we define delta hat T of phi as follows. And this is very similar to the definition of the categorical entropy, but in this case we use delta hat T instead of delta T. So this measures the and we also take the supremum over all objects in D. So this measures the exponential growth rate of this number. So how fast this number grows when n goes. And then the first main theorem is main proposition is that this entropy type invariant in fact coincides with the categorical entropy, and it also can be written as follows, more simple form. So in the original definition, we took the supremum over all objects in D, but this says that you don't need to take the supremum over all objects, but we only need to consider a split generator and the exponential growth rate of this number. And then the first main theorem is that now suppose on exact endofunctor gamma, which is a functor from D to the bounded derived category of K, and we assume that it satisfies some technical condition, and then this H hat can be written as follows. So what is good about these formulas, because so this formula says that we can interpret this entropy as this exponential growth rate of some linear of dimensions of some linear spaces. So we don't need to take a filtration of something to compute the entropy. So So this says that the entropy can be computed by some linear algebraic method. And in many cases, this is very, very interesting formula and interesting quantity, and we'll see that later. And also here we consider a covariant functor, and we can also consider contravariant case. And in the case, we need the minus sign here. And then for co-T structures, we can do similar things. And for now let B be a bounded co-T structure on D with finite coord, and we also define for an object E and a real number T, we define delta check T E as follows. It's almost same as the delta hat T, but in this case, we should take the infimum over co-T filtration. So because co-T filtration is not unique. So, and we also define another entropy type invariant. And in this case, for an exact endofunctor phi, we define H check T as this formula. So this measures the exponential growth rate of delta T check. And also in this case, we can prove similar proposition and theorem. And this also coincides with the categorical entropy. And this also can be written as a simpler form. And in this case, the theorem says that if we assume that an exact functor gamma satisfies some technical conditions, which is longer than the case of the T structure, but let me skip the details. But if gamma satisfies these conditions, then these categorical and these entropy type invariants can be written as follows. So it can be interpreted as some the exponential growth rate of dimensions of some vector spaces. So in this case, we can also consider covariant case, and in that case, we need to reverse the sign. And so finally, I'd like to apply this to the case of ST triples. So let's recall the definitions. So an object of D on object M is called a splitting object if it is a split generator of D and satisfies these conditions. So on K and M vanishes for every positive K. And then for a subcategory C and any object M, we define C like 0 and C like 0 M as follows. With this formula. And using these stations, we can define an ST triple. So ST triple is a triple A, B, and M, where A and B are fixed subcategories of D, and M is a shifting object of B, satisfying the following conditions. So following condition. So and well, and most important condition is today is the third one. This condition, the third condition says that A has a bounded T structure of this form. And as we will see soon, for an ST triple ABM, the category B has a bounded co-T structure. So we want to apply the previous results to such a situation. So let's see some examples of ST triples. So let A be a DG algebra, and then we can define two categories. One is the category of perfect DG A modules, and the second is the category of proper DG A modules. So here proper means that proper DG module means that DG module with finite total finite dimensional total convergence. And the first, let's suppose that the DG algebra A satisfies the following three conditions. And first condition is that the convergence of A vanishes for every positive K, and H0A is finite dimensional, and this category is contained in part A. So for instance, this condition is satisfied if A is smooth digit. So this diagonal bimodule is perfect DGAA module. And in this case, this triple is on ST triple inside per N. And the next example is kind of opposite situation. And now in this case, we suppose A satisfies the following two conditions. And the first is the same as before. And in this case, we assume that the total cohomology of A is finite dimensional. And in this case, people call A proper DG module. And in this case, this is to show that this inclusion hold. So this is the opposite to this situation. And in this case, this triple is also on ST triple inside DFDA. So what is the T structure on this category in this case? Because the selecting object is A, so if we put A to this place M, then this is just HK of E. Is A. So this T structure is the standard T structure. And so you have seen that for on ST triple AVM, we have a bounded T structure on A of this form, something like the standard T structure, and its heart is equivalent to mod and M. And we can also define a bounded co-T structure on B, and this defined as follows. And B get 0 is defined as the full subcategory of B containing M shifted by K for all non-positive K, closed on the taking extensions and direct summations. And likewise, we can define this one. And this is something like the standard co-T structure that we have seen at the almost the beginning. And then these two subcategories form a bounded co-T structure in B, and its cohort is at M. So, and the T structure on A and the co-T structure on B are orthogonal to each other in some sense. So let me explain that. Now let S1 to Sm be a set of objects of the heart, and this complete set of pairwise non-isomorphic simple objects. And we define M1 to Mn to be indecomposable objects such that M is isomorphic to M1 plus to plus Mn. And these are, of course, objects of the cohort. And so if we reorder M1 to Mn carefully, then we have this relation. So home K from M1 to Sj vanishes except the case where I equals to j and k equals to 0. So in this kind of orthogonal configuration, and then applying theorem 1 and 2, we obtain the following. So if AVM is on ST triple inside D, and phi is an exact autoequivalence such that phi sends A to A and B send phi sends B to B, and let me write S1 plus Sn by S. Then the categorical entropy of phi restricted to A is coincides with H minus T. So here it is minus T, and of phi restricted to B inverse. So they are, I don't know, they are same, but they almost the same. So I will explain why it is almost the same soon. And they also coincide with this quantity. And so in this case, the categorical entropy can be interpreted as the exponential growth rate of this number. So it is easier to understand than the original definition of the categorical entropy. And so how to prove this? So this can be proved by applying proposition theorem 1 to this case. So proposition 1 says that this holds, so categorical entropy coincides with H hat T, and by theorem 1 we see that H T hat phi A is limit of log of K comma A phi N G A to the minus KT. And because in this case gamma is this, so this is H on minus K M, and because GA is S, we put phi and S here. So we obtain this formula. And likewise, we apply proposition and theorem 2 to, okay, I will move this out to this functor and this is very general. So here this home and something, and here home something and S. So if we apply theorem 2 to this situation, we obtain the same quantity. But to obtain the same quantity, but we need to apply it to H minus T of the inverse functor. So in this way, we obtain the theorem 3. And some remarks. We call a triangulated category saturated if it is equivalent to the perfect Dirac category of a smooth and proper gauge category. And in this case, we can say something more. And it is known that if D is saturated, then for an exact auto equivalence, the categorical entropy at H minus T of the inverse functor is the original functor. So if B is saturated, this is just this one. So, but in general, I don't know, but I expect that this is true in general, but this is best possible you can say. Well, and this, the previous theorem can be thought of as an analog of the following famous theorem, and these are thought by THKK. If T is saturated, then the categorical entropy can be written as the exponential growth rate of the dimension of these homes. So this is almost the same formula, but here these two are the split generator of some category D, but in this case, these are also split generators, but M is in B and S is in A. So, and S doesn't need to be an object of B, and also M doesn't need to be an object of A. So this is slightly different, but the split is the same. And finally, let me explain some geometric examples. And so quickly, and now let X be a Liouville manifold. For instance, let X be a cotangent bundle, and then we can define two kinds of A infinity categories. One is the so-called rectified category, and indeed its objects are Lagrangian submanifolds, and which can be non-compact, and Morphism spaces are Fourier complexes, and it contains a subcategory called the compact Fourier category, and it is the subcategory of the rectified category consisting of compact Lagrangian submanifolds. And then we can consider their derived categories, which I write by d pi wx and d pi fx. And it is not hard to show that the following for let let Q be a simply connected closed manifold, and we consider the cotangent bundle of Q, and then is the triple of derived compact Fourier category and derived rectified category, and finally the cotangent fiber is on ST2. So we can apply the previous result to this situation. And so for instance, we can consider the following situation. So now let F be a compactly supported symplectic morphism of T star Q, and then because this is compactly supported, F sends a compact Lagrangian submanifolds to compact Lagrangian submanifolds. So it induces some auto equivalence of the derived rectified category, and it sends the derived compact category to itself. So if we apply the theorem 3 to this situation, we see the following. So the categorical entropy of F star is almost coincide with the restricted functor, the entropy of the restricted functor, and it can be written as follows. Yes, this one. So this says that because in square category, the dimension of the morphism space can be considered as something like the intersection number of these submanifolds. We can interpret the categorical entropy of F star as the exponential growth rate of the intersection number of cotangent fiber and the image of zero section under Fn. So yes, time is up. Thank you.